Okay, welcome Mr. Ghassan, Sajjad, Muhammad Al-Khafaji. Hello Sajjad, welcome. Okay, hello to all dears. Please let me share my desktop and begin this session. I'm very to be able to work with you again in this course, Real Analysis 2. And I apologize for the internet problems and the lack of classes in the previous weeks. Let me write this for you in Google Translate. Okay.
أنا سعيد بتغيير عملي معك مرة أخرى. أنا سعيد جدا بالعمل معك مرة أخرى.
And
أعتذر عن مشاكل الإنترنت وعدم وجود دروس في الأسابيع الماضية.
okay, do you understand? Okay, and I hope classes will be held in time from now on.
أمل أن يلتقي الفصل بانتظام في الأسابيع القادمة.
Okay. In this session, we will review the content of Real Analysis 1 lesson, okay?
في هذه الجلسة سوف نستعرض بعض محتويات درس التحليل الحقيقي 1. قبل ذلك دعنا نلقي نظرة على درس التحليل الحقيقي 2.
Okay, this is the content or syllabus of the course Real Analysis 2, okay? In this course, we express content such as this: sign measure and complex measure. You see the definition of measure that are real valued, okay? Real valued measure, positive measure. In this course, we see the definition of sign measure and complex measure. Total variation, Hahn decomposition theorem, Lebesgue integrability with respect to complex measures, not positive measures, okay? Radon-Nikodym theorem, dual of LP spaces, product of measures, Fubini's and Tunnelis theorem, Reed representation theorem, Fourier analysis. And we can discuss about these topics and contents by our time, okay? And you know many reference in real analysis. For example, Principle of Real Analysis written by Ali Prentice and Borkinshaw. And this book, that is our textbook in Real Analysis 1, okay? Integration, Real Analysis, written by Axler. Measure, integration, and real analysis. That we continue by this book in this semester again, okay? And other books such as Folland's book, Real Analysis, Halmos' book, Measure Theory, and other useful books that you can find this source and many sources in real analysis in internet, okay? Sorry, let me review again. This is the definition of sigma algebra. Suppose X is a set and S is a set of subsets of X. Then S is called a sigma algebra on X if the following three conditions are satisfied. Empty set belonging to S. Mr. Sajjad, do you have any question? Sorry, Mr. Sajjad, do you have any question? Okay. Do you have my voice and image? Dear students, do you have my voice and image? Problems? I'm very sorry. Okay. I write these sentences for you. Let X and S be a measurable space. Then A is measurable if and only if A belongs to S. Okay? Do you understand?
Can you do software quickly?
Okay, I'm very sorry for these problems. And we saw the definition of Borel subsets of real numbers. At the first, the definition of a smallest sigma algebra containing a collection of subsets. Suppose X is a set and A is a set of subsets of X. Then the intersection of all sigma algebras on X that contain A is a sigma algebra on X. Okay? So that if, for example, A is a subset of the power set of X, we can write S indexed by A or other notation, I write by this. S A intersection of all S such that S is a sigma algebra and A is a subset of S, or the intersection of this family all S such that S is a sigma algebra and A is a subset of X, is a subset of S, okay? The intersection of this family, intersection of all sigma algebra that contain A. Obviously, SA is the smallest sigma algebra that is contain A, okay? Contain A. Okay. Suppose X is a set and A is a set of subsets of X. I write this by this. A is a subset of P of X. Okay. Then the intersection of all sigma algebras on X that contain A is a sigma algebra on X. And this proof is very easy. And we using the terminology is smallest for the intersection of all sigma algebras that contains a set A of subset of X makes sense because the intersection of those sigma algebras is contained in every sigma algebra that contains A. This sigma algebra trivially is the smallest sigma algebra on X that contains A. Example, suppose X is a set and A is the set of subset of X that consists of exactly one element, all singletons X. X belong to set X. Then the smallest sigma algebra on X containing A is the set of all subsets E of X such that E is countable or its complement is countable. Okay? And other examples that you saw. And we express the definition of Borel set. The smallest sigma algebra on R containing all open subsets of R is called the collection of Borel subsets of R. an element of the sigma algebra is called Borel set. So that if in these definitions we consider, for example, x equal to r and this a equal to tau, or the set of all open subsets of real numbers, then SA is the sigma algebra of Borel sets. Okay, and A is a Borel set if and only if A belongs to this sigma algebra. Okay, we have these definitions too. Okay, so that if we consider A as the set of all open subsets of R, the smallest sigma algebra generated by this A open sets is called the sigma algebra of Borel sets. Sigma algebra of Borel sets. And an element of the sigma algebra is called Borel set. Okay, Borel set. R is a Borel set if and only if R is a member of this sigma algebra. Okay, and we have many examples. Every closed subset of R is a Borel set because every closed subset of R is the complement of an open subset of R. Every closed subset of R is a Borel because every closed subset of R is the complement of an open subset of R. Let me a minute please. Okay, sorry. And every countable subset of R is a Borel set because if B be this countable set, then be the union of these singleton sets, which is Borel set because each singleton set is a closed set. Okay, so that all of these are Borel, and since Borel sets are sigma algebra, this union must be a Borel set again, and other example that we saw. And the definition of inverse image: if f is a function from x to y and A is a subset of Y, then the set F inverse of A is defined by the set of all x such that f of x belong to A. So that x belong to the inverse image of A under F if and only if f of x belong to A. Okay, and we see some example and these properties for each f from x to y. We have these equalities. The inverse image of the complement of A is the complement of inverse image of A, and in inverse image of this union equal to the union of this inverse image, and the inverse image of this intersection is the intersection of this inverse image. And the proof of this condition is very easy, and we have this proposition, inverse image of a composition. Suppose f from x to y and g from y to w are functions, then the inverse image of A under this composition g of f equal to the inverse image of this set under F. Inverse image of A under G, then inverse image of this set under F. Okay, and the definition of measurable function. Measurable function. Suppose x and s is a measurable space. A function f from x to r is called s measurable or just measurable if s is clear from the context. If for every Borel set B, the inverse image of B under F belong to S. Okay? So that we have this definition. F from x to r is S measurable if and only if for each A in Borel sets the inverse image of A belong to S. Okay, this is this definition. And we know that we have a sigma algebra such as S on this X, and we have the sigma algebra of Borel sets on R. Okay, F from X to R is S measurable if and only for each A in beta. the sigma algebra of Borel set. Okay, sigma algebra of Borel sets. The inverse image of A under S belong to S. Okay? Don't have any problem in my voice and image, dear students? The voice and image are okay? The voice and image are okay? Okay? And this is the definition of S measurable function or measurable function. And the definition of characteristic function K of E. Suppose E is a subset of a set X. The characteristic function of E is the function Xe from X to R defined by this function rule. Xe of X equal to 1 if X belong to E and 0 if X not belong in E. Characteristic function, and this proposition, suppose X and S is a measurable space and F from X to R is a function such that the inverse image of these infinite intervals belong to S only for each A. Then F is a measurable function. For proving that this F is S measurable, we must prove that for any Borel set, okay, for any Borel set, let me, F from S to R is S measurable equal to this. For each A in the sigma algebra of Borel sets, the inverse image of A belong to S. Now in this proposition, we prove that this statement equal to this. For each A in real numbers, the inverse image of this infinite interval belong to S. And we know that these sets is a subset of Borel sets, so that this is a very weaker condition than this, because this is a subset of beta, not whole of beta. Okay, if we have this inverse image in S, then for each Borel set, this inverse image belong to S, and this is very important. Okay, okay. And Borel measurable function, suppose X is a subset of R. A function from X to R is called a Borel measurable if the inverse image of B is a Borel set for every Borel set. So that in our definitions, if consider from X as a subset of R to R is Borel measurable instead of S measurable, okay? If and only if for each B as a Borel subset of X, Borel subset, the inverse image of B is a Borel subset or belong to beta, okay? This line instead of for each B in S, okay, this inverse image belong to or for each B this B must be considered as a subset of R, okay? Then this inverse image belong to sigma algebra of Borel sets, or more exactly this is a Borel subset of X, okay? Borel subset of X for each B as a subset of R, Borel, the inverse image of B belonging to S. This is the definition of S measurable function, okay? F from X to R is S measurable, okay? Measurable. But this is the definition of Borel measurable. We have this difference for each B as a Borel subset of R. This inverse image belongs to S, but this inverse image must be a Borel subset of X, not this general sigma algebra, okay? Suppose X is a subset of real numbers, a function f from X to R is called a Borel measurable if this inverse image is a Borel set for every Borel set beta of R. And we see that every continuous function is Borel measurable function. And the definition of increasing function, composition of measurable function are measurable function, and if f and g are S measurable function, these functions are S measurables too, f plus c, f minus c, and f multiplied by g. And if g not equal 0 for all x, then this ration f divided by g is an S measurable function. Okay, and we see the proof of this proposition. And also, if Fn is a sequence of S measurable functions and Fn tend to F, then F is S measurable 2. F is S measurable 2. And the definition of border set on this extended real valued numbers. And we see that the infimum and supremum of measurable functions are measurable. And in the next section, we see the definition of measures. Okay, suppose X is a set and S is a sigma algebra on X. A measure on this measurable space is a function such as mu from S up to this interval, such that mu of empty set equal to 0 and mu of this union equal to this summation for every disjoint sequence E1, E2 up to the n in S. And this is the important property of measures. Important properties of measure. Okay, mu of this union equal to this summation. Okay, yes, do you have my voice? Welcome, Mr. Mashadi. We are reviewing the some contents of the real analysis 1. Okay, review some contents and definition in real analysis 1. Do you have any problem, dear students? I continue. Do you have any questions? Do you have any problem? Please answer.
Can you use software figures?
Dear students, do you have my voice? Yes or no? Not. You want my voice and image, okay? Okay. Okay. Let me a minute. سلام شبتی ارادت، من سر کلاس هم شبتی جان. کلید دست کی بود؟ پس بذار من کلاس هم 10 دقیقه دیگه تموم میشه میگم. کجا هستیم بنده خدا؟ من سر کلاس هم با این دوستان عراقی کلید دست کی؟ بذار من آقای چی رو من پیدا میکنم، آقای حضرتی رو بهش بگم. آها کلیدا دست چیزه. ببین خانم سرلک باید چیزی که اون دفعه خانم سرلک گفت اومد باز کنه. میتونی زنگ بهش بزنی؟ من سر کلاسم. معصومیه رو نه متصدیه. خب معصومیه نه مشکلی نه. بذار برای پناهجو زنگ میزنم میگم. چش الان زنگ میزنم. چش قربان. Okay, sorry. I apologize for this telephone. And this is the definition of measure, and this is very, very important. And we saw some example about measure that you can review from the textbook. Now, in any measurable space, if we add a measure, this triple is called a measure space, not measurable, okay? A measure space is an ordered triple x, s, and mu, where x is a set, s is a sequential algebra on x, and mu is a measure on this measurable space. And we see the proposition of measures. Measures are monotone if D is a subset of it, then mu of D is less than or equal mu of E, and mu of E minus D equal to mu of E minus mu of D, provided that mu of D is binary. Okay, and also for each sequence in S we have this inequality. Please note that this sequence is not mutually disjoint, okay, in general. And we have this property. Suppose x, s, and mu is a measure space and E1 is a subset of E2 up to the n, or this sequence is increasing sequence sets in S. Then we have this equality, mu of this union equal to the limit of these objects. Okay, and also we have this proposition: if this sequence is decreasing, mu of intersection equal to this limit, and this nice property: if x, s, and mu is a measurable space and D and E are elements in S with this property, then we have this equality. We have this equality, and definition of Lebesgue measure. We see the definition of outer measure, and we know that outer measures is not necessarily additive, but if A and G are disjoint subset of R and G is open, then we have this equality. In general case we have inequality in this equality. Okay, and also if R and F are disjoint and F is closed, then we have this equality again. F is closed or F is open. Okay, we have this equality, and not this equality is not holds in general, and this proposition suppose be it a subset, Borel subset of R, then for each epsilon there exists a closed set such as F such that this subtraction less than epsilon. And also this proposition, if A and B are disjoint and B is a Borel, we see the special case of this in the previous proposition. If B is Borel or closed, now if B is Borel set, then again we have this equality. Okay, there exists a subset of R that is not Borel set, and outer measure on R is a measure on Borel set. If we restricted the domain of outer measure in Borel set, we have a measure, and the definition of Lebesgue measure is the measure on this measurable space where beta is the sigma algebra of Borel set. Okay, and the definition of Lebesgue measurable set that pass this definition, and this nice proposition A is a Lebesgue measurable set if and only if we have these properties or these, and these properties are very useful for you, that we see the definition of this proposition completely. The set L of Lebesgue measurable subset of R is a sigma algebra on R, and outer measure is a measure on this measurable space, not whole of P of R, this sigma algebra. Okay, the definition of Lebesgue measure is the measure on this measurable space where L is the sigma algebra of Lebesgue measurable subset of R that assigned to each Lebesgue measurable set is outer measure. Okay, and pointwise and uniform convergence, that you can review these contents from the book. And the definition of integration with respect to measure. Okay, please let me review the definition of Lebesgue integral in the next session, and then continue property of Lebesgue integral in the next session. Thank you very much for your attention. I continue this from the next session. Okay? Do you have any questions, dear students? Do you have any questions? Okay? So in the next session we continue inshallah, and we can continue by the Lebesgue integral properties. Okay? Lebesgue integral properties. Okay? Inshallah يوم الخميس. Okay? يوم الخميس. Thank you very much for your attention, and goodbye for now. Goodbye.